Hello, my name is Quentin Broussard. I'm Assistant Professor of Clinical Sciences and Critical Care at California Health Sciences University. Today is day 2 of our discussion on acid-base disorders. So today the objectives are the same. We're still going to do a little bit of review about pathophys related to acid-base disorders. We'll be able to still identify acid-base disorders via a patient presentation. Our main objective today, however, though, is to utilize arterial blood gases, or ABGs, as well as serum chemistries to diagnose acid-base disorders. So that will be our main objective today. And then we can use all of the things that we know about pathophys identification via patient presentation and the ABG and serum chemistries to develop a therapeutic plan to manage an acid-base disorder. There are many different diagnostic steps to diagnosing an acid-base disorder, so we have 6 of them listed here. So we'll go over each of these steps throughout the presentation and apply it to an actual example. So it'll be important to get familiar with this process, as this process will be important to identify acid-base disorders based off of ABGs and serum chemistries. Again, we'll start with a patient case. We have FM, an 82-year-old male, presenting to the ED initially with ultramental status. Upon his admission, serum electrolytes and an arterial blood gas are obtained. So, as we said, the first step is to obtain ABGs, or arterial blood gases, and electrolytes simultaneously. So we did that here with FM's case. So step 1 is done. Now, here is the serum chemistries, or the basic metabolic panel that we have here. His sodium is 145, his potassium is 4.2, chloride is 102, his CO2, and this parameter is known as the bicarb. So it's essentially going to be the same as the bicarb on the arterial blood gas, is 15. So the important thing to remember about the CO2 value is that it's not the CO2 from the lungs. It's actually bicarbonate. They just label it as CO2. He has a BUN of 100, a serum creatinine of 8.2, and a glucose of 158. For his arterial blood gas, which was obtained via an A line or a radial artery, potentially, his pH is 7.34, his PCO2 is 33, his PaO2 is 80 millimeters of mercury, his bicarb on the ABG is 15, and his arterial oxygen saturation is 98%. So this was essentially step 1, is just obtaining these values. Now we'll go to step 2. Step 2 is to compare your bicarb from your ABG and your electrolytes to verify accuracy. Now what this means is essentially we're looking at the values from the basic metabolic panel for bicarb, which is 15 here, as well as our arterial blood gas, which is 15 here. Now, on a basic metabolic panel, the bicarb level is measured on the BMP. However, whenever you take an arterial blood gas, this bicarb level is actually calculated. And sometimes this calculation will be off. Now, if it's off greater than a quantity of 2 from the basic metabolic panel, the arterial blood gas may not actually be valid. You might have to recheck of an arterial blood gas. But for the purposes of most arterial blood gases, most of the time they will be within either 0 or 1 of the basic metabolic panel. So it's important that these 2 numbers match. For the purposes of whenever we use bicarb for any kind of analysis that we're doing, we want to use the serum bicarb because this is the measured value, not the bicarb from the arterial blood gas, which is the calculated value. Unless for some reason arterial blood gas is all that you have access to. And there will be some cases where you may get an arterial blood gas before you get a basic metabolic panel, or vice versa. So it's important to remember what the more validated one is, and that is the bicarb from the basic metabolic panel. So we've compared the bicarb and the electrolytes to verify the accuracy of the ABG, and we concluded that the bicarb and the bicarb from the ABG and the serum chemistries are the same, so it's accurate. Now, we need to calculate an anion gap. So, if you remember from our talk yesterday, we discussed anion gap. And the anion gap is our sodium concentration minus our bicarb minus our chloride. And with this equation, you always want to use the bicarb from the basic metabolic panel. So in this case, the anion gap is 145 minus 15 minus 102, which is the chloride. And whenever you subtract that out, you get 28 for your anion gap. Now, it's important to always do the anion gap, as this may indicate a potential anion gap metabolic acidosis. Though many times whenever you do the anion gap, your anion gap will actually be less than 12. So here we see that the anion gap is 28, so our anion gap is elevated in this case, so it's above 12. However, we don't know if it's an acidosis yet or an alkalosis, so just keep this to the side for the moment. The next step that we'll want to take is to determine if our disorder is an acidosis or an alkalosis. So acidosis is commonly associated with a pH of less than 7.35, and an alkalosis is commonly associated with a pH of 7.45 or above. So keep these numbers in the back of your mind as we look at our ABG. Again, these numbers here that are listed are the ones that you'll need to know for the arterial blood collection. So 7.35 to 7.45 for the pH. Also remember PCO2 is 35 to 45, and the bicarb is 22 to 28 for the normal levels. In terms of our patient here, our patient has a pH of 7.34, which actually falls on the lower end. Therefore, we have some type of acidosis occurring. So, pretty relatively simple. Just know where the numbers fall within the range. Now, sometimes you may have an acidosis that actually may have a normal pH, but it may be like on the lower end of normal, so like a 7.35, 7.36, or anything relatively under 7.4. So it's important to classify each of these as whether it's normal, low, or high. So in this case, the pH is low, so it's an acidosis. We've done step 4, which was declaring that the disorder was an acidosis based off of its pH. Now, we need to determine whether that disorder is respiratory or metabolic in nature. So remember, if it's a respiratory disorder, it's usually some kind of alteration in the PCO2 or the PaCO2, or a metabolic disorder, an alteration in the HCO3 or the bicarb. Now, whenever you look at most of these disorders, a lot of these disorders will have alterations in both. So it's important to figure out what the thing is that's driving this disorder. So if it's an acidosis, as we saw here, we want to look ideally for a high CO2 or a low bicarb. So we established that the pH of 7.34 was an acidosis. we'll take a look at our PCO2 here, which is 33, which, if you remember, our range for PCO2 is 35 to 45, so this PCO2 is actually low. Now, if you also look at our bicarb number, remember to use the bicarb from the BMP or the basic metabolic panel. That bicarb number that we have here is 15, and our normal range for bicarb is anywhere from 22 to 28, so therefore 15 is low in regards to that. So whenever we're thinking about this, we have a low PCO2 and a low bicarb. So the next step we'll do is we'll go to our acid-basis order identification. So as we mentioned, we have an acidemia because our pH was 7.34, and we also have low bicarb as well as low PCO2. And since the only option here is a low bicarb, then we have a subsequent metabolic acidosis, theoretically. So let's go back and look at our numbers. If we have that bicarb of 15 here, that bicarb of 15 looks like it's generating this acidosis here to occur as a result of low amounts of base. Therefore, we have a metabolic acidosis. Our last step in the diagnosis of acid-base disorders is to estimate compensatory response to determine if there is a potential mixed disorder. So remember what we talked about mixed disorders yesterday, is that mixed disorders are disorders that exist concomitantly together. So you may have a metabolic acidosis with some other type of acid-base disorder, whether it be a metabolic alkalosis, respiratory acidosis, respiratory alkalosis, or even another metabolic acidosis. Now, there are some formulas that you can use to help determine this. So, depending on what disorder you have, and for this case you have a metabolic acidosis, you'll want to measure the amount of compensation you have. So what compensation is essentially is if you have an alteration in either your PCO2 or your PaCO2, then what is your expected compensation for the other organ? So in terms of a metabolic acidosis, what we're essentially calculating here is we have a bicarb level that was generated by that metabolic acidosis. We want to know what the expected compensation is by the lungs. So what value should the PCO2 or the PaCO2 be in regards to this bicarb level that we have here that, remember, was 15. So if we actually use this formula is called Winner's formula. Depending on which acid-base disorder you have, you choose which formula you use. By using Winner's formula, we see that the bicarb was 15, so we input it into this formula, and we generate an answer of 30.5 plus or minus 2, which, if you actually break that apart, it's anywhere from 28.5 to 32.5. Remember, you're using that bicarb of 15 from the basic metabolic panel, not the bicarb from the ABG. So our PCO2 should theoretically be 28.5 to 32.5. So here's our answer again right here, which is the 28.5 to 32.5. Now let's look at what our PCO2 actually is. Our PCO2 is actually 33. So think about a metabolic acidosis. So your primary insult is that you have a low bicarb. And whenever you have a metabolic acidosis, the way to compensate for that is to try to expel CO2. So ideally, what we want the the CO2 to be to compensate properly to get us back to a normal pH is anywhere from 28.5 to 32.5, so on the lower end, so actually below normal. So we see our PCO2 is 33. That's really close to this compensation range, so you can say that you almost have full compensation here. It's almost practically there, and if you would round that 32.5, it would actually be there. However, there might be some disorders in terms of acid-base disorders where you either may not be fully compensated, you might have no compensation, or you might have too much compensation. And whenever those occur, that's whenever we start getting into the mixed picture. This one here, since it's practically within range, it being 33, and if you round this, 33 and 32.5 are essentially almost the same. We can see here that there's likely not a mixed disorder. And we'll talk about identification of disorders whenever the numbers actually fall out of these ranges a little more on day 2, as well as our lab day on Thursday. But in terms of mixed disorders, we're not going to be focusing on them as much. It'll be important to realize whenever you do have a mixed disorder, and usually that's whenever these numbers actually fall out of range here. So as you can see, we completed all 6 steps in terms of acid-base disorder diagnostics for using an ABG and electrolyte simultaneously. So let's go back to our patient case now. So we had FM, who is our 82-year-old male, presenting to the ED with ultramental status. We got his electrolytes and his ABG obtained upon admission. We determined that he had a metabolic acidosis from his ABG that we looked at previously. Now, kind of tying that in to the patient's presentation, sometimes you won't always have a full presentation to go off of. Sometimes you might just have the ABG, sometimes you might just have a serum chemistry, sometimes you might have a whole patient presentation and an ABG. Ideally, you would like more information than less, but sometimes in terms of critical care and emergency, you might not have all of the information because the patient is just presenting to you. But what if you found out eventually, later on in the patient's presentation, that he was actually the patient that we talked about yesterday in our day 1 talk that came in with the medical history of ESRD, for which he got hemodialysis 3 times a week but missed his dialysis session. This is actually the same patient here. So essentially what we did today was we classified the ABG of the patient, who we classified the acid-base disorder based off of his patient presentation yesterday. So as you can see, there's many different ways to recognize an acid-base disorder, as we talked about. There's the patient presentation, you have the ABGs and the serum chemistries, and you have the pathophysiology of essentially what's going on with the patient. So you should be able to identify acid-base disorders not only via the ABG, but also how your patient is presenting, or a combination of both sometimes, because sometimes some different causes may have different disorders that they can manifest as, such as the salicylates, the asthma COPD, as well as pneumonias. So going back to our slide from yesterday, now fully filled in, some of the tools that you can use are, as we mentioned, the patient presentation, the serum chemistries, particularly to obtain that bicarb number, as well as to get our anion gap, our arterial blood gas, which is very important in terms of trying to designate numerically what an acid-base disorder is. There's also another method called the tic-tac-toe method. I won't cover this method here in this presentation, but if you actually look at your readiness handout, I included a link which will actually bring you to a website where they have a link to a YouTube video where they discuss this tic-tac-toe method. And what this method does is it helps to categorize and classify some of these acid-base disorders, particularly if you're kind of confused about, when do you call something metabolic and when do you call something respiratory. This can help you out potentially. It's a short 14 to 15 minute video to help you classify some of this out. So I recommend that you listen to it, though it is optional. And then when trying to classify some of these acid-base disorders and you have an ABG, you might want to think of the acronym ROME, R-O-M-E. So whenever you think about ROME, you're thinking about respiratory opposite, metabolic equal. Because if you actually go back to our classification of the different acid-base disorders, if you have a respiratory disorder, you have alkalemia, which this would be an up arrow. Or, I'm sorry, actually, if you have a respiratory disorder, the arrows will be opposite. So, if you have a respiratory alkalosis, which is an arrow down on the PCO2, it's actually an arrow up on the pH, so a down arrow, up arrow, depending on what your laboratory parameters are. Now, for respiratory acidosis, it's increased PCO2 and a down arrow for the pH, versus metabolic, which is equal, so the arrows are actually the same direction. So for acidemia, your arrow is down. For metabolic acidosis, your arrow is down. For alkalemia, your arrow is up. For metabolic alkalosis, your arrow is up. So that's one potential strategy you can use to try to classify these different disorders. Though remember that it's important to understand the reason why these different alterations are actually causing the disorder. So only use it in case you're lost and you potentially get confused. Again, these are the references here. And if you have any questions, please feel free to email me. Thank you and have a good day.